This video is for Math 1325, and we are up to section 2.4. This involves what's called exponential functions. Exponential functions are backwards from what you're used to in lower level math. This is where the base is a positive number like 2, and the exponent has the variable, like x, as opposed to the other way around. If it was x to the second power, x squared or x cubed, those are the kind we're used to, like in high school math. Exponential, it reverses, and it's 2 to the x power. So this is a kind of a parent function to know. It turns out exponentials always go through the following 3 points on their parent functions. If you plug in -1, 0, and 1, you can always find these 3 spots. If you plug 1 in, anything to the first power is itself, so 2 to the first power is 2. Plug 0 in, anything to the 0 power is 1. And if you plug -1 in, 2 to the -1, that's a rule of exponents where you do 1 over 2 to the +1. A negative exponent has nothing to do with negative numbers. It just makes the base move to the other half of the fraction. 1 over 2 to the first is the same thing as 1/2. So an exponential graph goes through these 3 coordinates. -1, 1/2 is about there. 0, 1 is right here. That's a little bigger. And then 1, 2 would be about there. And this is a curve that goes through these 3. And it rises real fast on this side, and it levels off here. It has a domain of -infinity to infinity, all real numbers. You can always plug anything into an exponential function. The range, though, is 0 to infinity, not including 0. It never touches or goes below 0. That's actually a horizontal asymptote, y equals 0. So that's a basic exponential graph right there. And this is if the base is +2. If the base was +3 or +10, it just rises faster. This is called exponential growth when it rises left to right. If it goes the opposite case, you'll get something that come like this. That occurs when the base is between 0 and 1, like 1/2 or 1/3 or things like that. So that's called exponential decay, like a radioactive material that decays over time. Whoops. Okay, so first thing we want to do is solve log equations here in the section 2.4 homework. Solve for x as usual in algebra. 5 to the 5x minus 7 equals 625. So there are 3 kinds of these problems. The first kind is, notice that the base is a 5 and the x is up in the exponent. That's why this is exponential. So 5 to the 5x minus 7 equals 625. In the first case, you try to make the bigger base look like the smaller one. Sometimes you're able to do that. Sometimes you have to change both of them to smaller bases. That's the second kind of problem. And the third kind is when you can't change them to each other in any way, and then there's a way to handle that. So if you're going to try to make 625 look like a 5, the way you do that is start listing powers of 5. 5 to the first is 5. 5 squared is 25. 5 to the third is 125. And you keep going down this list hoping that you hit 625. Now, if you don't know what 5 to the third is, it's literally 5 times 5 times 5. That's 125. Or many calculators have a 5 raised to the third power. 5 raised to the fourth power. Bingo, 625. if I would have done 5 to the 4th, and let's say it was 725 instead of 625, if you pass this number up and it's not in this list, then you go to level 2 and you try to make both of the bases go smaller if you can. So I'm able to change 625 to be the same thing as it's equal to 5 to the 4th, so I can change it to that. Anything that's equal to something can be substituted out for it. So I can change 625 to 5 to the 4th since they equal each other. This is what you hope happens in an exponential equation. You hope you can make both of the bases the same. If you can, they in essence cancel out. Because the only way powers can equal each other, if the bases are the same, the exponents would have to be the same too. So you're literally just setting the exponents equal to each other. 5x minus 7 has to equal 4. Since the bases are the same, the exponents have to be the same. And they'll often do this where it doesn't come out exactly just because they don't want you guessing and checking. Somebody might try plug in 1, plug in 2, plug in 3, and hope they get lucky and find the answer. But they would never find this one because 4 plus 7 is 11. 11 divided by 5 is 11 divided by 5. Nobody would ever guess that. And yes, that's equal to 2.2, but you normally don't put decimal answers unless they ask for it. And in fact, it says right here in blue, type an integer or a simplified fraction. So they would not take a decimal answer here. It would just be wrong automatically. Even though 11 divided by 5 equals 2.2, if you put 2.2, they say it's wrong. Oh, they took it this time. Okay, that's weird. Sometimes they call that one wrong. But this is what I usually do is I'll try it another equivalent way and see if they take it or not. And if they don't, then you know you're not allowed to do that. It's a little surprising to me. Usually when they say type an integer or a fraction, they normally don't take decimals, but maybe because 11 divided by 5 was exactly 2.2, they did here. But I have seen times where they'll say type an integer or a fraction, and the answer might be 1/2, which we all know is 0.5 exactly. And if you put the 0.5 in, they'll say it's wrong sometimes. So best thing is usually whatever they say in the directions as we should do normally. Okay, so that was the kind where you could turn the bigger base into the smaller one. I'll just make up an extra example. Say you have 8 to the x equals 16 to the, I guess we'll just keep this simple, make this like 3. But it's about the bases, the 8 and the 16. So you always try to make the bigger base look like the smaller one if you can. Here you won't be able to, but 8 to the first is 8. 8 to the second is already 64. So I already skipped 16. That means I can't turn 16 into a base of 8. But maybe I can make both of them go to a smaller base. It turns out they're both powers of 2. 2 to the first is 2. 2 squared is 4. 2 to the third is 8. There's that one. And 2 to the fourth is 16. So you can change 8 to be 2 to the third. That replaces the 8. Now the to the x is still there. You can have a base to an exponent to another exponent. In fact, there's a rule of exponents for that. And then 16 can change into 2 to the fourth. But that's still to the third power. So some other rules of exponents. I showed you the negative exponent 1. 2 to the negative 1 is 1 over 2 to the positive 1. If you do like a 7 to the third times 7 to the fourth, that's 7 to the 3 plus 4. Not 3 times 4. It's 7 to the 7. The base doesn't change and you just add the exponents. If you get like a, let's do a 5 to the 8th divided by 5 to the 4th, this is 5 to the 8 minus 4. You don't divide them, you subtract them. 5 to the 4th. And then the final rule is if you get this, if you have 2 to the 4th to the 3rd, this is different than this where they both have a base of 7. 7 to the 4 and 7 to the 3, that's when you add them. But if you just have 2 to the 4 to the 3, it looks like you should do 4 to the third power, but you never do the rules of exponents the way they look. So that's where you multiply exponents, and you'd get 2 to the 12. 4 times 3, not 4 to the third. And this would be 2 to the literally 3x. 3 times x is 3x. So I made both of the bases the same, then they cancel out. You're left with 3x equals 12, so x would equal 4. So it would turn out that 8 to the fourth power, 8 to the fourth would be the same thing as 16 to the third is what that's saying. 8 to the fourth happens to equal 4,096. Apparently 16 to the third equals that as well. Yep. So that's what we did, is we solved for x. And this is the first two levels of an exponential equation. The first level, you try to make the bigger base look like the smaller base with powers of this. I was able to do that here. Level 2, you try to make both bases go down to a smaller one because you can't make the bigger one look like the smaller one. And then problem number 2 is actually level 3. This is where you can't do either of those two things. I have 2 to the x plus 6 equals 3 to the x minus 5. And these two bases are both prime numbers. And there's no power of 2 that's equal to 3, so you can't do 2 to the first, 2 to the second, you already missed 3. And they can't go smaller because they're already prime numbers. There's no other smaller base to go down to. So here's what you do when you can't make the bases the same. We're going to employ a log, which is what the next section is about. We'll deal more with logs next section. But if you put a log on each side of an equation, you can always do the same thing to both sides of an equation. We're going to see in the very next section some properties of logs, and maybe you remember this from college algebra. One property of logs is you can bring an exponent down in front. So I can have x plus 6 times the log of 2. That's the only way to get the x out of the exponent if you can't make the bases the same. Bring this x down, x minus 5 times log of 3. And now we're just going to solve for x. Think of log of 2. It's kind of like square root of 2. Square root of 2 is just a big, long, messy decimal that they definitely wouldn't take that as an answer. It turns out log of 2 is very similar. It's just a big, long, messy decimal. But it's really just some plain number. It's kind of similar to just having 2. If you just had a 2 here, you would distribute the 2 into the parenthesis. So you're going to do that here too. You're going to get x log of 2. That's all you can do when you multiply log of 2 times x. And then you get plus 6 log of 2. Distribute this one into here. X log of 3 minus 5 log of 3. Then what we do is there's 4 terms here. 2 of them have an x attached to them. And the other 2 don't. So you want to get stuff with x on one side and stuff that doesn't have x on the other side. So I'm going to leave this x log of 2 right here. I'm going to subtract this one over to the other side. I'm going to leave this negative 5 log of 3 on this side. And then I need to take this plus 6 one and subtract it over there. That'll make it minus 6. And the one good thing about this kind of problem is we don't care how messy the other side gets. The whole goal is to get x by itself. Since both of these terms have an x, that's the greatest common factor, you can factor out an x. And it just leaves log 2 minus log 3 equals that. And then you're literally going to divide both sides by all this stuff that's not equal to x because it's x times this stuff. Divide both sides by that. And this is a final answer many times. We don't care how messy it is. But this big mess right here, these are all decimals. There's a messy decimal for all 4 of these. Negative 5 log of 3 minus 6 log of 2, all divided by log of 2 minus log of 3. But this is considered what they call the exact answer. I think what this problem is going to want is they're going to want an exact answer first, and then they'll say, give me an approximate answer with a calculator, just so we can get an idea what it's close to, because it's hard to know what this is even close to in the form that it's in. But in upper level math, they always prefer exact answers. Usually I should say, at least. And don't put a decimal and say S for, but notice here it does say type an integer or a decimal. Do not round until the final answer, then round to 4 decimal places. So here's the issue. Even if you're doing a decimal here, we can't round anything. You don't want to type this first part into the calculator and get a decimal and round it, and then do this one and round it, and this one and this one. It'll throw the answer off. So what I'm going to do is I'm going to put parentheses around the top and the bottom and see if I can type that all in at once. So let me clear all this. Okay, so parenthesis. Put this here so I can see what I have. I need a 5 negative. Oh, I lost my parenthesis though. That's weird. Try that again. Oh no, it's there. Okay. It's just not showing up. Okay. That's weird. Okay, clear all this. Parenthesis, 5 negative. Okay, now the only issue is, let me see if I have graphing calculator might be better here. Oh no, that's not going to help. Okay, so well, let me do it this way first, and then we'll see how we can do it in here. But this is a case where a graphing calculator helps a lot more. So I have a graphing calculator right here, and I can type it the way it looks. So I can put parenthesis, -5, there's an LOG button on the side, -5 log of 3. Now when I type a log, I don't know how well that's showing up in the video, but when I type a log, the parenthesis pops up. So I need to close the parenthesis for the log of 3. Then -6 log of 2, close parenthesis. Then I'm going to close the parenthesis a second time, so that's the numerator of the fraction. Divided by parenthesis, now I'm doing a parenthesis in the bottom, log 2, close parenthesis, minus log 3, double close parenthesis. So this way I have a parenthesis around the whole numerator, I have a parenthesis around the denominator, and everywhere there's a log, I have an open and a closed parenthesis. So really what I typed in was parenthesis, -5. When I hit log, a parenthesis pops up, so then I closed it. -6 log, parenthesis, close it, and then close the numerator parenthesis. Then I hit the divided by, parenthesis, log, the parenthesis pops up, 2, close parenthesis, minus log, parenthesis pops up, close parenthesis, equals. This is the best way to get an answer where there's no rounding going on, because if you round each step of the way, then it counts it wrong. That's why they say do not round until the final answer. Then round to 4 decimal places as needed. So I'm going to be putting in 23.8046. The next digit's a 2. So then you don't have to add 1 to the 6. 23.8046. So with a graphing calculator, that's very easy to type in the cases where they do want a decimal. This was a case where they did want a decimal. Sometimes there's like a part A where they want the exact answer, and then there's a part B where they want the approximate answer, or they could just ask for the exact answer. Now the issue is, how would I do this if I don't have a graphing calculator? And that's where you might have to play with your calculator a little bit, but so the order of operations throws this off as the problem. I can't type it in the way I thought I was going to. So let me clear all this again. I think what you need to do is type in log of 3 first. So, and it's actually backwards in a scientific calculator. You type the 3 first, then you hit the log button. You get this messy decimal. Multiply that by -5. Okay, so that's this part here. So now minus, and I'm going to put 2 log times -6. And you have to type 6 negative, you even have to type that backwards. This is the entire numerator. So probably what I would do is write down, you're never going to write all those decimals down, but write down like 7 or 8 or 9 decimals. That should be enough. 579, 426, 426, 2996. So I did the numerator out to 10 decimal places. Now I can do the denominator a little more easily. 2 log minus 3 log. Here's the denominator. -0.176, 091, 259. Then I would have to divide these two. And the two negatives will be a positive, so I can just ignore that. 5.579, 426, 2996 divided by 0.176091259. And did we even come close to the same answer? No, it's way off. So okay, so something is wrong with it. That's why I wanted to do it the other way first to be sure. So it's probably the way I was typing those times on them. What if, maybe I forgot the negative on one of them, maybe not. Log 3 times -5. Okay, so that, you might have to do this. -2.38560 627. See, I think the issue was when I typed the whole numerator at once, as soon as I hit minus log 2 and then hit times, it might have subtracted that already. That's what I think happened, that's why it was wrong. So I have to do this one separately. Log 2 times -6. So then now I can just hit minus 2.383, if I can read my own writing, 60627. This should be the numerator. And see, it's different than what I got the last time. So yeah, that made a difference. It's -4.189. 786. And actually, I don't even have to write it all down because I'm just going to hit divided by this. So divided by 0.17609. Whoops, I did that wrong. Dang. Can I do that? Well, I was going to hope to get that without having, I hit a wrong button is what happened. Okay, so I guess I do need to write it down. 189,786,244. I'll round that to 244. So now I got to do it again because I hit this exponential button, or this factorial button actually. Okay, one more time. See how messy this is with a scientific calculator, but if this is all you have, then you wouldn't be able to do anything else, unfortunately. 756,244 divided by 0.17609. I went too high and hit this button instead of the 9. 91259. Does this equal 23.8046? See, it's still off even a little from there. So it got me closer this time, but we probably need more decimals is the problem. So that's always the issue here when they say do not round until the final answer, then round to 4 decimal places. So the only lesson there is if you're going to do this with a simpler calculator, you could, but you're going to have to be very, very exact on it. And if you do each part one at a time, you need to write down a whole bunch of decimals on each one. Not just like 8 or 9. That wasn't even good enough. I wasn't sure how that was going to come out, but the graphing calculator was much easier and got me the answer exactly. And then when I was trying to do it with a scientific, it was still off even in the end. Okay, so back to the graphs of exponentials, 2 to the x plus 3. See, this is what we were doing last time. Now we've in essence learned a new parent function here. This is the one I made up, 2 to the x. So the question is, what if you get a transformation graph that has 2 to the x plus 3, and it depends where the plus 3 is. If the plus 3 is up in the exponent with x, that affects the horizontal direction. And then you do it the opposite of the way it looks. If it was 2 to the x and a separate plus 3, then it would be a vertical shift. But this 3 plus 3 is up there in the exponent with x. So that's going to make it move to the left 3. This one moves left 3. This one moves up 3, if you were to get one like this. So you just take these 3 points right here and move them all to the left 3, literally. Same thing when we were doing the other ones last time. So it's not going to flip it upside down like graph B. That would happen if there was a negative in front of the 2. It looks like A's been shifted down. The one that looks like it's shifted to the left is C. So it's a little hard to tell. This is 10. So 1 would be right there. Here's 0, 1 right here. And that spot's moved over 1, 2, 3 right there. That's 3 to the left. And then remember we had 1, 2. This is a little hard because it's going by 2s. 2, 4, 6, 8, 10. So 1 is when you go halfway to the right. 1, 2 would be right there. Move that to the left 3, and each half interval is 1. So there's 1, back to the y-axis, 2, 3 to the left. So yeah, the 0, 1s move 3 to the left, the 1, 2s move 3 to the left. The other point would be hard to check because it was at a half, but that's the whole point, is it just moved to the left 3. Once you learn how the graph goes, then you just do the change no matter what type of graph you have. And this was the other kind I was talking about. This is called exponential decay. So if you have y equals 1/5 to the x power, and there isn't any like plus 3s or negatives or times anything, so this is in essence another parent function. You just need to plug in -1, 0, and 1. And you'll get the 3 points on your graph. And it's going to be a decay, so it's going to come down like this. So anything to the -1 power flips the fraction. It's going to flip from 1/5 to 5/1. Anything to the 0 power is 1, and anything to the first power is itself. And there's no shifting or transformations of any kind. So as usual, if you have a parent function, it goes through 0, 1 on any exponential. 1, 1/5. 1/5 is 0.2, so that's like real close to the x-axis. And -1 goes all the way up to 5. 2, 3, 4, 5, way up here. So this is exponential decay, and it's really dropping fast. And the opposite of this would be if it went upward like that. That would happen if it was 5 to the x power. And then you would go through -1, 1/5, 0, 1, and then you'd go through 1, 5. But this is 1/5. So when the base is a fraction like 1/5, then it's decay, it's not growth. And this is actually a cube root function, so it's not graph C. This isn't it, or maybe that could be it, except it's been moved to the right too far. So it looks like it's this one here, A. See how it went right through 0, 1, and it went through -1 and 5. And then it's hard to tell that this is 1 and 1/5, but that could be 1/5 right there. So this is graph A. Okay, now we got a transformation to do. So there is a 2 minus 4 raised to the negative x power. And this could be rewritten negative 4 to the negative x plus 2. I'm going to rewrite it like that on purpose. This is a negative that's not with x in the exponent, so that's a vertical reflection. This is a horizontal reflection because that negative is with x. Negatives multiplied in are reflections, and they can be vertical or horizontal, the same way you can have a vertical or horizontal shift or vertical or horizontal shrinking or stretching. The base is 4. So the parent function for this one is 4 to the x. And that's the one you'd want to graph. So it's going to go through 0, 1, like all parent functions do for exponentials. If x is 1, you would have 4 for y. So it goes through 1, 4. 1, 4, 0, 1. And then it would go through negative 1 and 1 over 4, which is 0.25. Negative 1 and 1/4. So you always do these three coordinates on the parent function. This is 4 to the x power. And then I need to do a vertical reflection, a horizontal reflection, and then move it up 2. Shift it up 2 because that 2 is not with the exponent. And the reflections would happen before the shifting up or down would happen. So first you could flip it upside down. A vertical reflection flips it upside down like this, so that these distances here are mirrored. Then a horizontal reflection would make this part go over here, and then this downward part would go like that. So this is both a vertical and a horizontal reflection, and now move it up 2. So it's going to be something like that, and maybe in multiple choice I can tell which one it is. It's definitely not that or this. See right there, and not that. The only one even shaped the correct way is C. And it got moved up 2 is why it came back above the x-axis. In fact, without the up 2, there's still a y equals 0 horizontal asymptote. If you just have a reflection over y or a reflection over x, the asymptote won't move. But as soon as you move the graph up 2, the asymptote moves up 2 as well. So the new asymptote is y equals 2. And this graph here had that. See how it's going 2, 4, 6, 8, 10. Right through 2 is where it's leveling off at. Okay, this is I guess they could have had this one earlier. I don't know why it's down here, but this is like the first couple of problems. I'm going to try to make the bases the same if I can first, and here it turns out you can. 3 to the x equals 1 over 81. Try to make the bigger base look like the smaller one if you can. So do powers of 3. 3 to the first is 3. 3 squared is 9. 3 to the third is 27. It's the next one. 3 to the fourth is 81. 3 raised to the fourth is 81. So I can change 81 to be 3 to the fourth. Now, what makes this problem different than the other one is that the bases don't cancel unless they're both at the same level. They either need to both be in the top or both in the bottom of a fraction. And right now, the 3 to the x is in the top, because you could put that over 1 if you wanted to, but the 3 to the fourth is in the denominator. So these 3's won't cancel out as is. But there is a way to make them at the same level using a rule of exponents. Do I still have it here? Yeah. It's just doing this rule right here backwards. Usually it's when you have a negative exponent, you want to change it to a positive by putting it 1 over. But if you had a 1 over a positive exponent, you could change it to the base to a negative exponent, and that would move it back up to the top level. So you're just going from this direction to that direction on this rule of exponent right here. So 1 over 3 to the fourth is the same thing as 3 to the negative 4. And in high school, especially, or algebra, they all often harp on students never leave a negative exponent in your final answer. But this isn't my final answer yet. Sometimes you have to use a negative exponent to get to the finish line. So I had to change this 1 over 3 to the fourth to 3 to the negative 4. They are equivalent to each other. And now the bases are the same, and they're at the same level, so now the bases cancel out. And x equals negative 4. I don't even have to solve for x. It's already by itself. But there could have been more stuff right here than just x, and I'd have to do some algebra to find x. But x is negative 4. So that was a good extra problem there to see what happens if the base is in the bottom. Then you can bring it up to the top with a negative exponent. Here's one where we should be able to make these bases both go down to a smaller one. And sometimes you could do different powers. It wouldn't matter which one you picked. What number are we on? This is number 7. 64 to the 5x equals 16 to the x plus 3. I can't make the bigger one look like the smaller one because 16 to the first is 16, and 16 squared is already 256, so we already bypassed 64. Powers of 8 would not work because 8 to the first is 8, and 8 squared is 64. I wouldn't get the 16 from that. But you could do either powers of 4 or even powers of 2. They're going to both work. 4 to the first is 4. 4 squared is 16. 4 to the third is 64. This would be easier, but you could do powers of 2 as well. It turns out 2 to the fourth is 16, and 2 to the sixth is 64. If you want to do powers of 2, that would work. So change 16 to be 4 squared. And then you still have that x plus 3 as an extra exponent. Change 64 so it's 4 to the third power. And then you still have this 5x here. So I'm going to have 4 to something equals 4 to something, and then the bases will be the same. I need to use the rule of exponents where you multiply the exponents, though, where you have a base and 2 exponents. That's when you multiply them. 3 times 5x is 15x. And this is literally the distributive property, 2x plus 6. You should do that first before you cross out the bases. Now the bases cancel, and I'm just left with a basic algebra problem. 15x equals 2x plus 6. And once again, it's not going to come out evenly. This time, I'm guessing they're not going to take a decimal this time because this isn't going to be a nice decimal. 13x equals 6. Divide by 13. And you get x equals 6 over 13. I kind of ran out of room there, but 6 over 13. 6 divided by 13 is a really messy decimal. So I'm guessing they wouldn't take this, and you should definitely not put it unless they ask for it. Type in integer or fraction now, they definitely won't take that decimal because it's not exact. So just leave it 6 over 13. Plus, that's easier to type anyway than a big messy decimal. So that's a case where the decimal would definitely be wrong. I would never be able to round that because it goes on forever and ever. So I made up one of those. I didn't know if it was there or not, but it turned out it was there. Okay, this is just a special case. I don't know if you've seen this before or not, but there's a special base called e. It's very commonly used in calculus. Negative 4 e to the negative 3x. And then the minus 2 is not in the exponent. It's separate. There's a separate minus 2 here. So we have some changes going on. But first, the key thing is the base is e. Now, maybe you don't know what e is. E is a special number. You know pi, how pi is 3.14? 3.14159, but then it's a big messy decimal. E is like that too. This calculator, this scientific calculator even has e right there. They do have pi too. See how pi is 3.14159, although it keeps going. It's just a long, messy decimal that never stops. E is similar to that. E is 2.718281828, but then it doesn't repeat after that. It looks like it's repeating at first, but it doesn't. So think of that as 2.7. It's approximately 2.7. Don't put 2.7 for the answer, but think of it as 2.7. 2.718, and it keeps going like pi keeps going. So if you had 2 to the x power, remember that one went like this, and it actually went through the coordinate 1, 2. Well, if you do 3 to the x, what happens is they all go through the 0, 1. 1, 3 is where 3 to the x goes through. It rises faster and falls quicker. That's 3 to the x. Well, 2.7 to the x is kind of in between, not exactly halfway in between, but it's about right there. So 2e to the x kind of goes halfway between, not halfway, but somewhere in between 2 to the x and 3 to the x. And it'll be somewhere in between here too. But it's the same basic shape as all of these. So this is a very special one, e to the x power. That's called Euler's constant. Euler was a Swiss mathematician a couple hundred years ago who worked with this. Euler's constant. If you say the name in English, because he was a Swiss mathematician, an English speaker might pronounce this Euler, but it was pronounced Euler, like the Houston Oiler football team that used to be here years ago, before the Texans came around. So Euler's constant. So once you know the basic shape, now it's just a matter of shifting things. So I have both of the negatives again. There's going to be both a vertical and a horizontal reflection because of the negatives in both slots. The vertical reflection happens in the negative that's not up in the exponent. The negative in the exponent is a horizontal reflection. The -2 is easy. That's shifting down too, although you'll do that step last. The 4 and the 3, these are stretchings and shrinkings. And the one that's not with x, you do that one like it looks. That's a vertical stretch times 4. So that's going to make it rise even faster. The 3 or the 2 or the 2.7 is going to get multiplied by 4 and make it way up there, like around between 8 and 12. And then this 3, normally times 3 makes things bigger, but they are always opposite when they're horizontal. This is a horizontal shrinking. Horizontal shrink. And instead of times 3, think of it as dividing by 3. You're dividing x coordinates by 3. So the 1 will be shifted over to 1/3 is what will happen. I'll just make it thinner and closer to the y-axis. So although here this will be easier than maybe the other problem because we can just put all these changes in. So you click anywhere on the graph, and then you want to click your exponential tool button. And remember, I didn't know what they wanted last time, but you literally can click anywhere. It doesn't matter because it'll draw the parent function for you. This is e to the x right here. Notice it's going through 0, 1, and then it's going through 1, about 2.7. Okay, so then we're just going to change all this until we get each thing. I've got a reflection over the x-axis. That's a vertical reflection. I've got a reflection over the y-axis. That's a horizontal reflection. And then I have a vertical stretch times 4. So if you click this, it'll say 1, and then you just move it until it's 4. That'll make it 4 times as tall or thin, or tall or short, I guess, because it's going downward instead of upward. And then there's a horizontal shrink of 1/3. Well, let me go down there. No, that's weird. Okay. Okay, so it won't let me put 1/3 for that. That's weird. Okay. And then there's, well, we need to do that before we can do this one. There's also a vertical shift of -2, so I'm going to eventually move this over to -2. But now the only issue here is the limitation of the computer here. I would like to put 1/3 for that. I would like to have a 1 divided by 3, not a times 3. Because of this 3 right here, you do the opposite. It won't let me go to 1/3 though. 1/3 is 0.33 and I can't, it jumps from 0 to a half. Now a horizontal shrinking has the same effect as a vertical stretching. So I'm wondering if after I did a 4, what if I also do times 3 more and make this 12? Is that even possible? No. Okay, then I'm not sure how we're going to get this 0.3 in there. Okay, vertical shift -2. Now the only issue is it's going to say this is wrong because I didn't do the horizontal stretch because I don't know how you do it when it won't let you get to it. Okay, well, let's just get this wrong then. And see, all I'm missing is the horizontal shrinking. It's making it move closer to the y-axis, but okay, well, maybe. See, this would help because now I would have an option for this one. So very similar deal. So I'm going to do the parent function first. So I got both reflections. Check both of those boxes. Those are the two negatives. There's a vertical stretching times 4. So move that to 4. And then there's a horizontal shrinking of a half. 1 divided by 2 instead of times 2, you're dividing by 2. And I can actually go to a half. So, and then I got my vertical shift. This time it's +3, so I need to go up 3, +3. Okay, so I don't think this is 2, but let's try that and see. Okay, well, that's weird. It's supposed to be the opposite of the way it looks. So I guess that's how we could have handled that last problem. But this times 2 is normally a divided by 2 when you're doing horizontal changes. That's kind of weird how that was the same. Okay, so when you get one of those, number 8, similar question. I don't know if it's a programming issue or not, but you're going to have your two negatives. You're going to reflect both of them. This times 3 is a vertical stretch times 3. This times 3 is supposed to be a horizontal shrink, but they're doing it as a stretch for some reason. So just move that to 3 too. That explains why I couldn't get to 1/3. And then this -1 is a vertical shift to -1. And there is no horizontal shift. You would need a plus or a minus up in with the exponent. So that's how you can get that right, but it's strange that it's not divided by 3 instead of times 3. Okay, well, anyway, here's number 9. Okay, here's a business application of exponentials. If you invest money in some kind of an account, and you can get your account compounded at different periods of time. It can be annually, semi-annually, which is twice a year, quarterly is 4 times a year, monthly 12 times a year, or even continuously. This is how rich people gain so much money, and their interest grows so fast. If you got like billions of dollars, like a Elon Musk or a Bill Gates, and how they make so much money. So the general formula for this is A stands for the future value of your money. It's a little weird they use A for that when future value doesn't have an A in it really other than in value. A equals future value. P is the present amount, or what they call the principal, how much money you actually invest. And then there's a 1 plus R over N. R is the interest rate. N is the number of times you do it per year. So 1 for annually, 2 for semi-annually, 4 for quarterly, and so on. And then the exponent has the N again, and then times T, the number of years. So this formula will work on all the parts except for the last part. Part A I'm doing annually. So then N is 1. we're going to find the interest earned on a $15,000 investment. So that's your present amount. You're presently going to put $15,000 in a bank. It's going to sit there for 5 years. 4% is your interest rate, compounded as follows. So the present amount is $15,000. 4% is 0.04 as a decimal. Don't forget to move it over twice. Then first I plug in 1. And then we're doing this for 5 years? Yeah, 5 years. So 15,000. And you're just following order of operations. So I'm doing the parentheses first. Inside the parentheses, I would divide first and then add second. 0.04 divided by 1 is 0.04. Plus 1 is literally 1.04. I can do this 1 times 5 and get 5. So I need 1.04 to the 5th power. I had to do the exponent first, and now finally multiply by 15,000. So my $15,000 investment will grow into the future. 5 years from now, my money will be worth $18,249.79. Sometimes they like dollars, sometimes they like cents for the answer. Let me check. Round to the nearest cent. This is not the answer, though. This is the future value, $18,249.79. This is what your account is worth 5 years from now. But you put $15,000 in there. So you need to subtract 15,000 because that's how much was your money originally. If you subtract your original amount, that's how much interest you made. But it's basically free money. So you're getting over $3,000 of free money just by leaving it in there for 5 years. And you still have your $15,000. It's safer than maybe like putting it under your pillow or under your mattress. It's safe in the bank and can sit there, and then you also make money off of it too. 3249.79. That's annually. So when you switch to semi-annually, all that changes is the n is going to become a 2. So this slot and this slot will both be 2s, but everything else is the same. So in part B, the future value is your $15,000 investment. There's always this 1 that's part of the formula. 1 plus R over N. So now it's 0.04 divided by 2 this time. And then 2 times 5. So just these 2 2's changed. Everything else was the same. The 15,000, the 0.04, and the 5. Those could change if you go to another problem, but since they're giving me part A, B, C, D, I get to use the same numbers every time. So you got to do the parentheses first, and you got to divide first. That's easy to divide, though. 0.04 divided by 2 is literally 0.02. Then you add the 1 that's part of the formula. So you get 1.02 for the parenthesis part. 2 times 5, the exponent's 10. So raise this to the 10th power. And now multiply by 15,000. So your money was now be worth $18,284.92. Subtract your original 15,000 to get the interest. So the interest will be 3284. See how it's a little higher? 3284.92 if I round to the cent, because this 1 you have to add 1 to it. So by having the interest calculated twice a year instead of once a year, it got me an extra $30 some. That's not that big of a deal, but it's partly because I only have 15,000. Try putting $1 billion in the bank and see how fast that grows. What if I go to quarterly? Quarterly is 4 times a year. There's 4 quarters in a year. So part C, the only thing that's going to change, the 1 plus will still be here. quarterly means the denominator's 4 and the first part of the exponent's 4. But everything else is the same. So again, there's this 1 plus right here that's part of the formula. So 0.04 divided by 4 is 0.01. So you'll get 15,000 times 1.01, and then 4 times 5 is a 20th power. So 0.04 divided by 4 is 0.01, plus 1 is 1.01, raised to the 20th power, and now times your 15,000. By doing this 4 times a year, and now subtract your 15,000 initial investment, now you've just earned $3,302.85. 3302.85. So again, it's going up like another $18 because of that. So the lesson here is the more often they calculate the interest, the faster your money can grow. If you're the person investing, you want it calculated as much as possible. If you're the one borrowing the money, then you want it done lesser than as often as possible. So monthly, the only thing that changes on monthly in Part D is you're going to put a 12 in the denominator and in the first slot of the exponent. And now things can get a little sticky decimal-wise. 0.04 divided by 12 may not come out that nice. Maybe it's not that bad. See, it's a big, long, messy repeating decimal. So now add 1 to it. 1.00333 repeating. 5 times 12 is 60. So I want to raise that to the 60th power. And then multiply by 15,000. So my money will be worth $18,314.95 in the future. If I deduct the 15,000 that I put in the bank originally, then I get this much free money, 3314.95. Add 1 to this 4 and make it a 5. 3314.95. So again, it went up by about $12. Okay, continuously, if you're constantly earning interest, and that's how the rich get richer and richer and richer, there's actually a separate formula for continuously. The future value of continuous interest, it does have the P, present value, but instead of multiplying by 1 plus R over N to the NT, and this is good because we saw this a second ago, it's multiplied by E, that 2.7-ish number, E raised to the RT. In fact, this kind of reminds me of that Pert shampoo. There's a shampoo company called Pert, P-E-R-T. This always reminds me of the shampoo. That's how I can always remember this formula easily. So what if you invest $15,000? E again is that approximately 2.7 number. The interest rate is 0.04 and the time is 5 years. .04 times 5 is exactly 0.2. This calculator has an E button, so you should push that. E raised to the 0.2, because you should do the exponent before you multiply. Order of operations, you would do this exponent before you would multiply. Now multiply by 15,000. Now it's 18,321.04. Subtract your $15,000 that you placed in the bank, and you've now earned yourself $3,321.04. Next digit's a 1, so you don't have to add 1. 3321.04. Again, that's about $7 higher than the previous one. It keeps getting a little higher. So that's the point of problem number 9. is as you calculate interest more often, and the best you can do is constantly calculate it, then the money grows a little better. And if you can do a higher investment, if you make the investment higher, if you do the time longer, if you get the interest rate higher, all of those can make it go higher even. Okay, last thing in 2.4, we have growth of a certain species. Remember exponential growth, exponential decay? That's the two concepts here. So bacteria or species, even humans, we grow exponentially. The human population, it doubles every 30, 40 years or so. And it would grow, it would have already grown maybe past the point that the earth could handle, if not for all the wars and diseases that we have. But all animals and bacteria, they grow exponentially, actually. The growth of a certain species in millions since 1950 closely fits the following exponential function. Now, the only issue is t is the number of years since 1950. So it's 3000 e to the 0.0166t. That's exponential. It's got a base of 2.7-ish. And then the exponent's got the variable. What would the population of the species... No, the population of the species was 3,552 million in 1960. How closely does the function approximate this value? So what we're going to do is we're going to plug in for t. T is the number of years since 1950. So to go from 1950 to 1960, that's a 10-year span. So that means t is 10. So you need to plug 10 in for t. Do the exponent first, 0.0166 times 10 is 0.166. It moves the decimal over. Then you're just going to do e to that first, because we got to do the exponent before we multiply. This is now similar to that continuous compounding of interest. So I need e to the 0.166 power. E raised to the 0.166. Then multiply by 3000. And then when I press equals, we want to see how close it is to this 3552. 3541. So it's close. It's not extremely close, but it's pretty close. 3,541 versus 3,552. When you're in the 3,500s and you're off by 10, that's not a huge difference. And then you'd have to round. They're rounding to the integer. So since there's a 7 here, that would round this one up to a 2. So that's why it's 3542. It's not 3042. So B is definitely out. So 3542, A and C both have that. There is no D. Okay. I would say this is a fairly close approximation, because you're talking millions too. It's only off by 10 million out of over 3.5 billion, actually. That's a fairly close approximation. I wouldn't say that it's not close. Okay, now approximate the population in the year 2000. So all you have to do is figure out how many years 2000 is from the year 1950. That's off by 50 years. The year 2000 happened 50 years after the year 1950. So that means you plug 50 in for t this time. So 0.0166, that's the original exponent, times 50 for t. Came out to 0.83 exactly. So now I need to do e to the 0.83 and then multiply by 3000. E to the 0.83. Oops, can't see that. E to the 0.83 times 3000. So now if I add 1 right there, round to the whole number, so you have to add 1 to this 79 and make it an 80. 6880. 6880, which, since that's over 1,000, that's actually a billion. 6,880 million is actually 6.88 billion. but all I did was plug 50 in and then put it in the function. And then finally estimate the population in the year 2015. So that's another 15 years past 2000. So then that means t is 65 instead of 50. So similar kind of deal, put a 65 in for t. 0166 times 65, 1.079. And now I got to do e to the 1.079, e to the 1.079 times 3,000. Now it's up to 8.8 billion, but they want millions here. So the 2 is not high enough to add 1. We're just going to leave it 8825. So in another 15 years, it went up 2 billion in the species. Okay, so there's a couple of applications that involved exponentials. And this one is more of a science thing, but number 9 was a business setting. And we got 100% on 2.4, so we're done with that. And then if I come over here, all of those are checked. So 2.1 through 2.4, those I'm done with now. We got 3 more to go, 2.5, 3.1, 3.2, and then the review. I have added more here now. There's a 3.3 through 4.5. And a second review already, and you'll see more of these populate throughout the semester. So I'm going to be working on the 3rd unit soon as well, and not that we need it anytime soon, but they're starting to populate in there. So we're halfway done with this unit, 2 weeks of the class, and then over the next 2 weeks we're going to be finishing this and doing a review. So I'll see you next time for section 2.5.